dealing with the second major consequence of Bayes' theorem. So we did the first one, which was uniform boundary principle. Today we would like to do second, third major consequences of Bayes' theorem. So the next result that we would like to do is a hugely important result, and it's beautiful also. It's called the open map theorem, open mapping theorem. So the open map theorem says something pretty interesting actually. Again, there are different versions of it. You see, what you call, different statements for open map theorem. They all are equivalent. That's what the key thing is. So the theorem says that if E and F are two Banach spaces, and T is a map from E into F actually. And this map is, of course, linear bounded. Okay. And subjective. Not necessarily bijective. So it's linear, bounded, and subjective. If this is the case, then there exists a number A positive such that for each G in F, there exists an F in F such that the norm of the F can be estimated by A times norm of G, and TF is equal to G. The image of F under T is equal to
F is an E.
And obviously F is an E. So you already said it.
No, you said it is an F. So.
Oh yes. Must be an E. So what do you think that what the theorem is telling you? Would be your interpretation of the result actually. What's so interesting about this theorem?
F is bounded. F is bounded.
F is bounded. So, okay. What essentially it is saying to you, that if you have a linear bounded map, which is surjective, okay, then you can find, so like for every G in F, you can find an F in F, okay, such that this and this hold. But the question is that how can I interpret this and this? So if I say for every G, there exists F such that TF is G. So what does this show actually? What does this show?
Subjectivity.
This kind of a subjectivity. Okay.
Sir,
So essentially what this theorem is telling you, okay, is that if T is continuous and left bounded and it's surjective, okay, then for each G in F, I can find kind of an approximate preimage actually. So for G, I can find a preimage F actually, okay? But it's not necessary that this preimage would be, so I'm calling it an approximate preimage actually. Can you see a kind of an approximation here? So, like this thing is showing to you preimages. So just think about it. If F is bijective, then for every F here I can find an E. For every G here I can find an F. Okay, so there will be no approximation. And if T is just subjective but not injective actually. Okay, so for the sum F, somehow you can find preimages, okay, but those images and preimages and their norms are somehow related in this manner actually. Just like a size of one can be estimated in the terms of another actually. Okay?
Sir,
And there is, okay, so there is another way to interpret this basically. I can also say that if T is a linear bounded and surjective, then T is an open map actually. And what do you mean by an open map? So it's kind of a map which maps the open sets into the open set. So you also quite often see basically this as a statement of open map theorem actually, and therefore you call it an open map theorem. Okay? But one thing is that that's a kind of a characterization of your open map. Figure it out. It's fun to think about it. Before getting into the proof, I like to remark one thing. Think about it, what will happen if T is injective also? That is, T is a bijection. So what's going to happen?
T inverse is open there.
Huh?
T inverse is open there.
T inverse is open map? No, I'm saying that okay, T inverse could be an open map, but there is something that we can follow from here actually. So in other words, first of all, the T inverse exists actually. That's one of the things. Okay? And if the T inverse exists, what would be the relationship between, so it's like if TF is G then, and T is bijective, then T inverse of G is F actually. Okay? And hence from this inequality I can see that this would be T inverse of G, I can estimate, so it's like for every preimage I can estimate this as norm of G actually. No, norm of G. Okay? Why? Because F is what? F is preimage of G. And what is this guy showing to you? Is it going to be something interesting? Think about it. T inverse is bounded actually. T inverse is bounded. Okay? So hence, we have an immediate corollary of this result. If this result is true, okay, we say that if T is linear and bounded from E into F, okay, and T is bijective,
and D inverse is bounded.
bijection, then T inverse is bounded actually. Okay. So you can treat this as a proof of essentially following from the result. And this result, this simple corollary has a name as well, and it's called a bounded inverse theorem. It's called bounded inverse theorem. There is something which is very crucial in this thing. Obviously, if I want to apply this result, then my E and F must be Banach spaces actually. So implicitly I am assuming that in this result that both E and F are Banach spaces. Okay? Banach spaces. Is it making sense? Okay. And you know, you can read the example, I'm not getting into it. It's a pretty simple example which says that that if you drop the Banachness or the completeness, okay, from any one of these spaces, okay, then this result is no more true actually. Even though you have a, you know, even though T is bijection and linear and bounded, still you T inverse is not necessarily bounded. Okay? So in other words, this completeness assumption is crucial actually. So we can't give up that actually. Okay? So if the one of the spaces is not complete, okay, then you know, okay, just quickly write this example that if you take E to be C01 with infinity norm, you take F to be C01 but 2 norm, okay, and you take the identity map actually, okay, from E into F. So the first question, which of these is not complete?
2 normal.
Norm is not complete. Okay, so the 2 norm space is not complete. So somehow, you know, we lose the, what do you call, completeness from here. Alright. Now, what we can see actually, that this I is linear and bounded, but its inverse is not bounded actually. Okay? So, for details, just see the book. Not getting into it, too much details actually. So it will be kind of a counter example, that if you drop completeness from any one of these spaces, then you can. Okay? So in other words, I can show that for an inverse, there is a sequence, okay, in this space, okay, which converges, but its images do not converge here actually. Okay, so that's what you can show essentially. Is it making sense? Now, here is another corollary of this result, okay, and it's a pretty nice corollary. Corollary, okay, of the result, which says that let E be a Banach space. So these are the small results which we have to keep somehow in our head, because these can be quoted at any time. Anyway. So let E be a Banach space with respect to, okay, one of given 2 norms actually. So imagine you have 2 norms, okay, maybe this and this, one of given 2 norms, this and this, okay. and this norm is not an L1 norm and not a L2 norm because this E is an abstract space actually. Okay. So I have a Banach space which is, which can be a norm of a Banach space as this norm or this norm actually. Okay. And imagine that one of the norm is weaker than other actually. So in other words, think about it. So you have a Banach space, okay, say under one of these two norms, and one norm is weaker than other, okay. Then the second norm would be also weaker than the first. In other words, the both norms are going to be equivalent. Okay. So in other words, on a Banach space, you can't have two non-equivalent norms. They are going to be always equivalent. Essentially, that's what it says. Okay. All right.
सर C01 with respect to two norm तो है, लेकिन with respect to infinity वहाँ पर वो जो one है.
So E is a Banach space with respect to. No. Okay. So there's a slight difference between here. I is a map from E into F actually, and so don't you know that these two norms are equivalent to each other? What's wrong with the so if they are equivalent, so if it is complete with respect to one norm, then it must be complete with respect to other norms as well. Either one of the
One of them
norms.
is weaker than the other, that we know, not the equivalence. एक weaker है दूसरे से, वो हमें पता है, पर equivalent है ये नहीं, मतलब वो ये नहीं है equivalent.
Okay, but
So the infinity
The Banach space with respect to these two norms.
yes. Okay, so here is the key thing actually. So it's like a E is okay. Let me finish with this, and then you're gonna see actually that it's like this is an example where you have E to F actually. Okay, and we have and bounded which is E to F actually. While we are going to have here from E to E. Things from E to E actually, not E to F somehow. That's a good point to reflect. Anyway, so if there exists an M positive or non-negative such that so like for example, so the two norm can be estimated as M times norm 1, okay, then the two norms and one norm are equivalent. Okay? So they are equivalent. E is a Banach space. Okay, so here's a one-liner proof. So if I take, say for example, I as a map from E with one norm into E with two norm, okay, and what? So can I say that this condition is equivalent to saying that this operator is bounded? Okay? So this condition projection. So it's like if you take the I of f in 2 norm, so you can estimate this since this is true in the terms of the norm 1. So this is the bounded map actually. And it's also linear. So it's linear and bounded from E into E. I is always a projection. There's nothing wrong with it. Identity. So what's going to happen? Then obviously I is same as I inverse actually. I inverse is. And if this is the case, by the way, I inverse is mapped from where to where?
A to E.
And this corollary is telling me that I equal to I inverse is bounded actually. And what is the meaning of I inverse being bounded actually? The I inverse being bounded means that the F1 norm, so it's like that is there exists, okay, M prime, which is non-negative, such that F1 norm can be estimated by M prime times
F2 norm.
F to the 2 norm. And this completes the rule. This completes the rule. I think there is something fishy.
Sir, हमने दिखाना था example लेता है.
There is something fishy. Alright. I think what he is somehow missing is that with respect to both given norms actually. This must be true. Otherwise, like this example fits in. Okay. And even to apply this result, you need a completeness of E and F both actually. If one of them is not complete with respect to one norm, you can't apply that. So I think this must be written there, but there is something wrong here. So don't always believe what is written in. So it's always good to reflect actually. Okay? Anyway. We have a duster. Is it making sense? So here's an open mapping theorem. And there are two beautiful corollaries. One says that if T is linear bounded and bijective, then its inverse is bounded too. So it's like a bounded inverse theorem. And you have another corollary which says that if you have 2 norms under which E is a Banach space, then and like one can be estimated in terms of other, like one is weaker than other, then the both norms are equivalent. Okay? This is what the result is telling us. Now, I want to get into the proof of this result, but before proving this result, I would like to prove what? I would like to prove a lemma.
सर ये if and only if हो जाएगी ना corollary, क्योंकि already हमने देखा हुआ है कि अगर 2 norms equivalent हो तो वो Banach हो जाएगी. नहीं.
What do you mean by where you want to put? Where you want to put if and only?
काशी
Anyway, let's move ahead. Now, there are several ways to prove this open mapping theorem. Okay? So, I have found Marcus' proof pretty interesting. It's elegant, simple, and less computationally complex. Otherwise, you can see most of the proofs of open map theorem, they get messier, a lot messier. Okay. So here's a lemma. So what does this essentially this lemma is telling us? So this lemma is telling us that if a map is not surjective, but it's kind of approximately surjective. So if it is approximately surjective, okay, then it is going to be, what do you call, then for every element in codomain you can find, okay, for every element in codomain you can find an approximate pre-major. Okay, and this approximate is pretty meaningful. So that's what this lemma is saying, and then this becomes just a simple corollary of the result. All right. So let E comma F be Banach spaces. And let T is a linear bounded map from E equal to F. And here is an hypothesis actually. So it's like this hypothesis should be very carefully understood. That suppose there exists a Q between 0 and 1, so it's like a number between 0 and 1, and a positive number, a non-negative number 0, such that for every G in F with norm less than or equal to 1, there is F in F such that norm of F is less than or equal to A, and norm of image NG is less than or equal to Q. Okay? So let's reflect upon this first technique and then write the third part. So I have two Banach spaces and a linear bounded map. But this linear bounded map is not an an ordinary linear bounded map, but it's approximately surjective. What do you mean by it's approximately surjective? So precisely writing that there is a number Q and A between 0 and 1, such that if you take any G from the codomain with norm less than or equal to 1, you can always find a preimage, roughly, a rough preimage, such that this preimage can be controlled by A, and the difference of the preimage and G can be controlled by Q actually. So it's not exactly equal to Q, but its difference is less than or equal to this number Q, which is between 0 and 1 actually. So therefore, we are calling it its approximate surjectivity, because this TF is not exactly a preimage of G actually. Okay? So it's like a F is not a exact preimage of G, so it's an approximate. So they are different. So they have some difference actually, but that difference can be controlled by what you call the Q actually. So that's an additional assumption on T. That's an additional assumption on T. Now I'm going to write the conclusion. Then Is it making sense that I'm saying that T is approximately surjective? Okay? Then, that will help. Then for each G in F, okay, there is F in E, okay, such that the F